Okay, so I will bet that every single one of you had this experience at least once. So you want to go out of the house to work. You open your weather forecasting app. You see a sunny icon with just 10% chance of rain. Therefore, you're leaving your umbrella next to the door. And then, after 10 minutes, the weather looks like this. You will probably go and blame your weather forecasting app. But your weather forecasting app is okay. The problem, most likely, the main reason for this mistake was clouds, as clouds are the largest uncertainty in our climate and weather predictions. This has to do with two factors. The first one is the fact that clouds are very small and chaotic, and therefore very hard to model. The other reason is that clouds has a huge influence on climate and weather. And actually, just a 3% increase in the amount of cloudiness all around the world will completely offset the effect of our carbon dioxide emissions. So what makes clouds such a huge game changer? This has to do with a term called albedo. So albedo is the percentage of sunlight reflected from objects. Generally, bright objects reflect more sunlight than dark objects. And while white objects reflect all sunlight hitting them, meaning they have an albedo of 100%, black objects doesn't reflect sunlight at all, therefore has an albedo of 0%. This is why on a hot Israeli summer, we would prefer wearing a white t-shirt because it absorb less light and therefore will get heat less. Similar to the shirts, we can measure an albedo for Earth, which is around 30%. Not similar to the shirts, the Earth's albedo is not homogeneous, but is actually composed out of three main components. The first one we can see here is the dark blue oceans that, because of their dark color, has an albedo of just 10%. The second component is the land. We can see that the land is a bit brighter and therefore has an average albedo of around 30%. The third component is clouds. Clouds we can see in this picture, and I think we understand from our everyday life that are almost white and therefore has an albedo of more than 50%. And therefore, they are the real game changer when it comes to albedo. So why do we care about albedo so much? This has to do with the fact that the sunlight is the source of energy of weather. Therefore, the albedo of Earth control almost completely how much energy does the weather has. So in my research, I compared the albedo of the northern hemisphere, which is everything which is from the equator northward, and the southern hemisphere, which is everything from the equator southward. The main difference when you observe these two hemispheres is the fact that the northern hemisphere has double the amount of land than the southern hemisphere. Therefore, this fact has a large influence on albedo, because the contribution of the surface albedo, meaning the land plus the ocean, is higher in the northern hemisphere by about 11%. However, when we look on the albedo of Earth from satellites, we find an albedo symmetry, meaning that both hemispheres has exactly the same albedo. And this is a phenomenon that is already observed since the 70s. So how can it be? This is again due to clouds. The southern hemispheres, it turns out to be cloudier, exactly such that the albedo of both of the hemispheres is exactly the same. This is very unlikely to happen by chance because this phenomenon is observed for decades. This is kind of like balancing a pencil on its tip. It might be a coincidence, but it's more likely that there is some kind of a trick or a mechanism behind it. And therefore, we deduce that cloud must somehow know what is the surface albedo of Earth. Therefore, our research question was, how do clouds know what is the surface albedo of Earth? Or, in other words, we can relate to this phenomenon as this causality change. So the lower southern hemisphere surface albedo is somehow causing more cloudiness that balance the initial difference. To start uncovering this mystery, let's look on the yearly average clouds all over Earth. As we can see, clouds are definitely not uniformly distributed, but are actually concentrated in hotspots. This structure of hotspots reminds astonishingly the structure of storm activity on Earth. Moreover, the storm activity is also stronger in the southern hemisphere, which makes storm activity a very good candidate to connect between the surface albedo and the cloud albedo. Storms are much easier to predict because they are bigger and better understood theoretically. So, if we will understand how the storms are affecting the cloud field around them, maybe we can use the predictability of storms to add to the predictability of clouds. And this is exactly what we did in our research. So how did we do it? We locate storm, we divide the storm by their strengths, and then we put a box around them and record what was the cloud field around them. And then we average all of these maps in order to obtain knowledge of how does the average storm affect on the clouds around it. So this is the result we got. We found that the strength of a storm almost completely determine the amount of clouds around the storm, and that the amount of clouds around the storm is strongly increasing with the storm strength. So this is very nice. And the next step that we did is we want to both prove that this really has predictability and prove that the storms are the things that connect between the surface albedo and cloud albedo. So what we did, we used these curves that we found and these formulas that involving this curve and the difference in the statistics of storms between the northern hemisphere and the southern hemisphere to calculate what are we expecting the difference in clouds to be based only on the storm data without the knowledge of clouds at all. And we found a calculated difference of 15.7%, which is almost the difference that is actually observed by satellite, which is 14.1%. And this proves that storm activity is the thing that connects the missing links that we looked for the connection between the surface albedo and the clouds. So to sum up, I would like to quote from a 1901 paper about weather predictions that I think really highlights how much progress we made in the last century in the field of atmospheric science. So the quote goes like this: "The anxiety of farmers with regard to their future crops has led them from time to look about the natural sign, as though the animals and even the trees know more about the laws of nature than man himself." So taking you back to my first slide, we definitely have now tools which are better than the tools that trees and animals has to predict the weather. However, until we will completely solve all the small details, I will still take the umbrella with me. So thank you very much.
Thank you. Oh.
Hi, thank you very much. What do you think causes more storms? Jonathan Katzenelberger from the Weizmann Institute as well. What do you think
causing more storms
in the southern hemisphere?
So first of all, the exact reason why the southern hemisphere is stormier is an open question. There is actually only barely studied because it's a very hard question. Because there is a lot of things. So it's true that when you're looking on the overall energy that the weather has, it's completely determined by the incoming solar radiation. But the way that the energy distributed between the different components of the atmosphere is very, very complicated. And it's kind of a question that is very hard to tackle. I think there was the first ever paper about this published now. And I had a glimpse on the data that it's based on, and I think it's not even close. I think we have a general understanding of why is it true. First of all, the fact that the southern hemisphere has more oceans means that it's absorb more energy. So it means that it has more energy for the weather. The thing is that it's a bit hard to connect to how storms work, because just in one word, storms doesn't care about the amount of energy they have. They care about the temperature difference. It's the temperature difference, and it's not so easy to connect how does the energy exactly flow from the fact that it absorbs more in oceans to the storms? So this is an open question currently.
Hey, thanks for the presentation. It was very interesting. My name is Israel Gabay from the Technion, mechanical engineer. And my question is about the reason that cloud moves. You present a figure that show causality between the cloudiness and basically more cloud around the storms. And storms, it's usually a very strong wind, right? And clouds move because the winds. So if there is a lot of winds in the area of the storm, it's not in the, I don't know, in the out of the reason that clouds are located more near storms. It's not have to be like that. This is the question, basically.
Let me just decomposing your question a bit. So there was one thing about the causality and one thing about the wind. So the causality is coming from the fact that these storms, there is a difference in scales between storms and clouds. So while clouds has like a characteristic scale of about 1 kilometer, these storms are thousands of kilometers wide, like thousands of kilometers wide first. And you have also the same thing with time scale. So while a time scale of a single cloud, when we are seeing a single cloud in the sky, it has a lifetime of about 1 hour, while the storms has a lifetime of about 1 week. This means that these storms are like way higher in the hierarchy of scales. And therefore, it is really hard to imagine how clouds directly controlling their storms. They have a feedback on storms, and this is something that is currently widely like a current field of research. But generally, it's the storms that control clouds, not the other way around. And this is because of these scales. You can think of how does a small thing control such a huge thing. And the other thing about the wind, so these storms, you need to imagine them as, think of the most extreme winter day in Israel. So like extreme winds, a lot of rain, very cold temperatures. So these are the storms. So they are actually associated with winds that can get up to like 50 kilometers per hour, 60 kilometers per hour. So it's actually, they are characterized by a very vigorous mixing of the atmosphere. And they are actually one of the main creators of clouds over Earth.
Thank you.
Hi, thank you. It was super interesting. I'm Oriane. I do philosophy of science in Tel Aviv. So isn't it like super surprising that the two hemispheres have the same albidity? Albedo.
Yeah.
And then do we know anything like about the history of this? Does it change over time? Maybe like with the plate tectonics, so long time scales, do we know, is this a kind of תכונה יציבה of planet Earth, a stable feature?
So thank you for the question. This is a great question. So first of all, it's extremely surprising. One of the things that's surprising about it is that it's only the albedo which is symmetric. The temperature distribution between the two hemispheres is not symmetric. The long wave, so we have a budget, so we have the short wave and you have the long waves that's going up. The long wave is also not symmetric. The precipitation, the rain is not symmetric. Almost nothing is symmetric. So it's extremely surprising. These measurements, this phenomenon is so this is for the first part. The second part is that this phenomenon is very hard to measure and very hard to model. So we really need the satellite measurements, the real satellite measurements in order to really incorporate, to really capture it. And also, we can reproduce them in models. So we can't reproduce them in our, so if you are thinking, the state-of-the-art models is the one used for climate change predictions, we can't represent this phenomenon in climate change predictions. And even, that's enough at this part. And it's kind of something that is really making more advancements in this field very, very hard, because we have one simulation that shows this phenomenon, which is Earth's current climate as we measure it. We can't reproduce it at all in our computer simulations. We can't really like going back to like paleoclimate, like past climate and stuff like that. We don't have the precision to actually capture such a thing. So the answer is no. That we can only measure it in the last 50 years from the satellite era.
Hi, Michal from Brain Sciences Weizmann Institute. Thanks for your talk. It was fascinating. I was curious about something you mentioned. You've mentioned in one of your first slides. You said that the amount of cloudiness is in affects or is in association with the CO2 offset. And I was wondering whether you could elaborate more about it or maybe explain the mechanism.
So it's not, this is kind of like a demonstrative tool of the power of clouds. They are not in association. We are not really sure how does, we actually think that the amount of cloud will decrease with increasing carbon dioxide emission, although we are not sure. Clouds are the main uncertainty, as I said, the main uncertainty in our climate prediction. So we are really not sure. One thing that it is relevant in this sense, that when we are thinking about because clouds has such a huge influence on Earth's climate, when we are thinking about geoengineering, so like intentionally changing the weather of Earth, clouds are the main candidate to be affected because they are quite easy to be affected in. For instance, we have like the Yodita Kesef experiment here, which is like you just throw particles into the air and then you just change the microphysical processes within the clouds. So there is many ideas of how to manipulate the weather with clouds. Although on the one hand they are very hard, they are very easy to be affected. On the other hand, because they are so chaotic, it's really hard to predict what exactly will happen if we will manipulate the clouds. So I hope this answers your question.
Eitan, Architecture Technion. Actually, my question was exactly on that topic. We see this industry, right, in the last like 5-10 years of producing clouds, which is, no? I see like newspaper articles about different companies that try to produce clouds.
This is
to recreate clouds.
Maybe I don't know on like
maybe it's like a false.
I think it's for. I think it's. So I know that like speculation industry, not speculation, like the like flat earth and stuff like these regions. So they constantly blaming the governments to manipulate clouds, but it's not.
There's no such thing.
It's it's like generally geoengineering now. It's like on the. So it was like completely a taboo until a couple of years ago. Lately, there is a lot of influential like climate and policy people that say, okay, it's a bit dumb to like completely take out of the table geoengineering because we are unintentionally do geoengineer because of our carbon dioxide emissions. So there are plans to start experimenting with this stuff, but this is very much on the plans side. And currently, I don't know of any large-scale cloud manipulation thing that is going on.
Last question.
It was actually also exactly on topic. So I think I'm just going to comment. I have no prior knowledge. I just saw like a documentary issue on it. But I think it's called cloud seeding maybe, or maybe something.
That's what you're discussing. But it's not new. Like Israel, I think, doing it since the 80s or something. Yeah. It's like a very old ideas that didn't really take off.
So maybe if you could discuss sort of I think you started discussing it earlier on, like the dark side of it, of not really knowing. Does it influence your research in some way? Or is it just so sidelined or so, like...
it's so small scale. Like when like all the pictures that I showed you are like very much not small scale; they are very large scale. Like I'm looking on all the clouds on Earth. So this small experiment has almost like no influence on my research at all. Yeah.
Thank you very much all.